So welcome everybody to this online event, which is organized in the context of AeroNet Marie Curie project, which is about in-flight connectivity in integrated terrestrial and non-terrestrial networks. We've got in this public event um, five speakers. We'll start our first presentation with Professor Simeon Hanzinotas, who is a professor at University of Luxembourg, and he's leading SICOM research group, and he's going to give a talk on direct networks in 6G and TN. Simeon, over to you. Now we are moving, let's say, to the final presentation in today's event, which is the presentation by Dr. Saptasi Ghosh from Digital Catapult. So he will make a presentation with respect to network automation in 6G. So Saptasi, over to you.
Yes. Thanks, Tasos. Give me a moment. Let me share my screen. I hope you can see my screen.
Yeah, if you can use, that's good.
Do you see the main display or?
Yeah, that's good.
It's good, right? Okay. All right. Give me a moment. Okay. Thanks, everybody, for joining. My name is Saptarshi. I am a visiting research fellow at NSBU and a future networks technologist at DC. I mainly work in 5G orchestration. So in this presentation, I'm going to talk about how orchestration can look like in this edge cloud space continuum. And in order to do that, I will model this problem to a specific kind of mathematical model that I call self-organized knowledge-defined networks. It's an extension of the software-defined networking stack with a knowledge component on top of it. I'll also discuss where in the SDN stack we can find overlap with the 5G SDA architecture. And this would actually help us to move towards release 19 and release 20 specifications, especially a concept called network digital twin. So starting off with the agenda, I'll first start with the basis of network intelligence with a bit of evolution history, where the standards from different sources like 3GPP, ETSI, ITF, they all come together. How the protocol stack looks like when we combine them together. How the mathematical model would look like, because this is where the optimization algorithms will run. And then an instance of that model would be routing as a service. This is a concept that we've been working for quite a while now. We have some results at the moment. I'll also demonstrate those. I have a plan to show a live demo. I have a notebook running with some of the components here and there that will give you a sense how an SDN looks like in action. And then looking forward to the state of the art of AI native telecoms, what are the theoretical and the practical aspect of it, and then I open up for the question and answer. So network intelligence, when it comes to our mind as orchestrator or orchestration engineers, we think about the figure on the top right. Let me just change this to laser pointer. So think of two customers communicating over a layer 2 fabric. And this is a layer 2 fabric for a reason we will see in a moment. Mostly this fabric is comprised of switches, and these switches are programmable in nature. They don't carry any control plane on top of it, very light control plane for the switch operations, but not for flow management. The flow management information comes from a controller which will oversee the whole switch, and it will simplify the topology management at a scale. The knowledge comes from a reasoning entity which communicates with the controller. So for example, you can think of a large language model or similar sort of intelligence which communicates with the controller and tells the controller by judging the network state, what action is feasible, what action is optimal. And based on that, those actions are translated into network configurations. And these switches gets configured from the controller based on those configurations. So here, for example, the customer A wants to communicate with customer B, and there are two possible paths. the reasoning agent can rank which path is more feasible than the others. Now, the problem of pathfinding in almost real time is not new. This is a domain of routing. But what it gives an extra edge from the reasoning point of view is knowing the network's behavior. And this is what we're trying to model in this presentation. So my goal for this discussion is to kind of modeling how a dynamic graph can be used for learning and training a model from which we can derive reasoning. So an operator would communicate with the controller and will provide tasks. These tasks are quality of service sensitive. So this will go into the controller and communicate with the reasoning agent to figure out the rest of the operations. The concept of network intelligence initially came up back in 2003 from David Clarke's paper, A Knowledge Plane for the Internet. And it was a time when SDN wasn't invented. So it has some concepts which are no longer valid anymore, but the concept of having a reasoning engine on top of a network operation is still valid. 4 years after network as a service, this paper was proposed by Paulo Costa from ICL, and his point of view was to give the cloud users the ability to control networks. Now, when, for example, as a cloud user, you go to, let's say, AWS or Azure, I get the flexibility to choose storage and compute, but not on the networks unless I kind of reserve networks. This is mainly coming from the fact that the rigidity, which is ingrained in the network infrastructure, is very high, and they're very much protocol dependent. So on-demand changes are not very flexible most of the time. This should be at 2017, not sorry, it's typo. So 10 years after, Cisco and other colleagues, they came up with the concept of knowledge-defined networking, and this cites back to the work of Clarke, and they extended it with a more SDN kind of instance. And a recent work that has come up, which is this unified KP. This is a unified knowledge plane concept, which also extends the idea of a 5G SPA. Now, during this time, also another concept was introduced by the Focus Lab in Germany through the Open 5G Hub project. And this concept called organic networking. The idea is you can think of a network topology as an organism. So it grows, it shrinks, and it also heterogeneously grows. So part of the network may grow differently than the other part of the network. In such a network, it is difficult to sort of manage the whole network from a single orchestration policy. So we need a bit of heterogeneity in that. So the two concepts that kind of will pave the path of this discussion is first, how do we handle the dynamics of a network? And how can we learn from the dynamics? Moving on, starting with the amalgamation of different standards. So I'll mainly focus on two standards. One is the RFC 7426, which is the software-defined networking standard. This is RFC, so it is defined in the IETF nomenclature. Software-defined network, as we all know, it has three layers: data plane, control plane, application plane. Data plane is also known as forwarding plane or infrastructure plane, which is mainly responsible for forwarding traffic or forwarding flows. A control plane communicates with the data plane with the OpenFlow protocol, and an application plane communicates with the control plane to REST-conf. We also call them NBI, or northbound interface, and southbound interface, or SBI, respectively. Apart from these two interfaces, occasionally you'll also see a netconf interface from the application to the data plane. Now, there are certain switch operations which are not covered in OpenFlow. OpenFlow is mainly responsible for manipulating flow information or flow tables. Now, information like creating VLANs, turning on and turning off of interfaces, these are not covered with OpenFlow instructions. And especially telemetry, sometimes interface level telemetry is not covered in OpenFlow protocol. So for those, we need a bypass, and sometimes netconf is used for that. Now, on the top of the SDN, we propose a new kind of a layer. And this is not just we propose, also there are evidences from various works in the literature that kind of stacks the knowledge plane on top of the SDN three-layer architecture. The communication between the knowledge plane and the application plane is through standard 3GPP compliant protocol families like RESTful APIs or PubSub. And the job of the knowledge plane is to extract informations from the states that the application plane collects from the controller. And based on those state changes, the knowledge plane derives certain inference. These are the inferences which will be used by the network intelligence to derive configurations based on a certain situation. Now, the bottom layer here, you see a typical 5G RAN core architecture. We have users connected with the G-Node Bs with UU interface. There could be XN interface between the G-Node Bs. And the G-Node B is also connected to the 5G core with end-to-end N3 interfaces with the control and the user plane respectively. And the user plane has UPFs, which connects to the data network or internet through N6. And the DN is basically a best effort service network. So when you send packet into that network, you have no control on how do you want to manage the traffic. For that, 3GPP introduced from release 16 N9 interface. And N9 is an inter-UPF interface. For specificity, it runs a UDP tunnel, and through it runs a protocol called GTPU, or GPR Understanding Protocol User Plane. And these GTPU tunnels are also marked with quality of service identifier, namely 5QI index. These indices also carries some constraints regarding bandwidth, delay, and jitter. So whenever these packets flow through these tunnels, we can specify at what quality of service those packets will flow. So this opens up new use cases like private 5G and industrial automation by leveraging this N9 interface. Now, because N9 is a logical interface, we need a layer 3 and layer 2 forwarding plane for this. And this is exactly where the amalgamation comes between SDN and the 5G SDN. So because the data plane of SDN is layer 2, we can steer the traffic of this N9 interface through the layer 2 fabric. And this fabric can then be managed by the upstream controllers, applications, and the knowledge. So with this vision, we will move forward that how the various standards and architectures which are suggested from these two standards can be combined to realize an unified architecture where software-defined network can control transport part of the 5G end-to-end. So an extension of the knowledge-defined network, we published a paper back in 2022. These are more details description of how the KDN may look like. We have added an extra layer called the overlay plane that abstracts the device-specific interfaces from device-agnostic interfaces for the controllers. Now, this figure is a bit old because the time of writing this paper, transformers were not there. So the only reasoning that we performed here was based on RNN. Now these RNNs are replaced by transformers. They both can predict sequences, but transformers don't face the problem of exploding gradient and vanishing gradient problem as the RNNs do. So you can think of the base model is almost the same. The reasoning engine is different in terms of the current design patterns. And this was a work that was contributed to the Sonnet project. Another project that I worked from the DC's perspective is the Reason project. This was a flagship 6G project led by University of Bristol. And here we introduced a concept called task-oriented networking. So if you recall the example I gave on network intelligence, the operator provides task to the network. Let's explain what task is. So this is a very busy diagram. We don't need to get into the individual details of it. You can see some feeder links for the satellites and all that. These are 3 layers of operations: infrastructure, control, and cross-domain control. So let me explain what cross-domain control actually is. Think of a service which is, excuse me, think of a service which is comprised of multiple microservices. And these microservices are hosted in different data centers. Now, based on the resources available on those data centers, we might not choose every services to be delegated to every data center. For example, one data center might have a lot of GPU resources. So microservices that might need GPU resources can prioritize those data centers. So as a result of it, what we get is a disaggregated variant of a microservice architecture, which is placed across administrative boundaries. And these administrative boundaries can be defined as data centers for providing services and ISPs for providing transits. So question is, if these microservices may also contain quality of service requirement between their communication, how would we orchestrate those links? So it's a series of work. So the one of the work that we published, the full architecture, then we focused on the cross-domain architecture, that how a customer can send a CSLA, which is a customer SLA, to a cross-domain orchestrator or CDO. And the CDO breaks down the task into smaller tasks and then delegate this task into the underlying inter-domain orchestrators or IDOs, which are specialized for doing certain specific type of tasks. And then these IDOs are connected to each other through ISPs. So you need to also provision paths between these ISPs so that this quality of service between the services are also satisfied. We then also worked on the IDO part, and we developed our own platform. This is the respective publications you can see coming as text. We then optimized the reconciliation of this cloud native architecture. And a recent work is orchestration on this transit infrastructure that was published this year in UCNC. Now let's focus a bit on this cloud native orchestration of transport network works, because this is going to be the basis of our following discussion. So the design looks like this. We are conceptualizing a microservice which represents a transit autonomous system. So a transit autonomous system communicates with two endpoints or two or more than two endpoints over networks, and it can process information based on certain quality of service specified in the flow between those two endpoints. In the example, what you see are two domains running, like for example, two VMs, and they are communicating with two different VLANs. And these two VLANs are allowing traffic to enter and exit from something called a transit package. Inside a transit package, we have a router running, which is this FR routing, free range routing. It's an open source routing package. And this routing application is extended with a couple of extra features: an admission control feature, a traffic shaping feature, and a forwarding logic. These three will expose capabilities in the upstream controllers to dictate what quality of service we want to enforce in that particular router. So when a flow enters in the router, we can now, using the admission control and the traffic shaping, we can control the amount of bandwidth it gets access to, because obviously it's not the only flow that will go through this router. So as a result of it, we can create many of such instances of these kind of routers, and we can put them in different data centers, and we can create a traffic engineer tunnel between them. And through this, we can create a topology which may look like something like this. An overlaid topology of UPFs, and these UPFs are running N9 interfaces which are traffic engineered, so we can say a flow for let's say the A1 and A2 user pair enter to this pink link, and it takes a different path compared to the green link. And this is done through a policy-based routing principle. So these policies are derived from somewhere, which would be this network intelligence aspect of extracting policies from a reasoning engine. and then embed those policies inside the layer 2 fabric. We achieve a very high degree of reliability, scaling the flows, scaling the time scale that is not achievable in best effort and just a shaped link. So the overall model would look like this, that we will be having some communication infrastructure, which would be ISPs, for example, and these ISPs will mediate between data centers, which would be having computation infrastructures. Now, each of these infrastructures will be managed by their own orchestrator. So a service domain IDO will manage the compute infrastructure, and the transit domain IDO, which will manage the communication infrastructure. Both these IDOs, they will advertise their capabilities, and this is basically taken from the HC's network slicing architecture. So each of these IDOs will advertise what are the capabilities they can offer, and these capabilities will go and get stored into a database or a catalog in the CDO. So the capabilities for the service is service domain is basically different type of resources it has access to, for example, GPU, CPU, storage, memory. But for the transit domain, the advertisements are of slices. So what are the different type of slices this domain can offer? And this is very much dependent on whatever the infrastructure it has underneath and what are the provisioning which is done on those infrastructure. Now, based on the user request, which is CSLA, as customer SLA, the CDO will not only break down the services into microservices and delegate them into the compute infrastructure, but will also choose the most feasible transit domain to make the communication possible between those services. All right. So moving on from here, and this was a joint work with BT, and it was funded by Reason and the SustainNet project. So for more information, you might follow their public documentations and deliverables. Now, looking into slicing, from the 3GPP TS 28530 document, we find the definition of a slice, which is a mapping between a service to a subnet. So a service is an abstract entity that is sometimes defined in terms of HC standard, a service graph. So a service graph is a graph, presumably a DAG, and it has nodes and edges, but the nodes are microservices and edges are constrained links. So I can say that node 2 and node 1 are two, let's say, Kubernetes services or microservices, and they communicate through a service mesh. And the service mesh is given with a particular constraint that the latency should not exceed certain milliseconds and the bandwidth should always be above certain Mbps. So these service graphs then gets enclosed into something called service profile. And a service profile also includes something called ingress and egress point. So it tells where the source of the traffic would be and who will consume the traffic. Now, based on this HC's transport network slicing architecture, the idea is the tenant would create this service profile and it will give it to a network slice provider or an NSP, where the NSP will consult with a resource database, which is populated by advertisement from the underlying network slicing agents. They will advertise topological information, resource information, and based on this database, the consulting database, the NSP will craft something called an NSI or a network slice instance. And this NSI will then get delegated into the NSAs into subnets. So that is the mapping function from a service, which is an abstract entity, and a subnet, which is more of a layer 2 or layer 3 overlay network. Typically, this is done by traffic engineering. And in the next slide, I'll explain what is the actual protocol map between these three layers. So in Reason, what we did, we added a layer in between. So you see some new component got added. And the first thing that we did was decoupling of the tenants from the NSP. So instead of the tenant is tightly coupled with a given NSP, we put a flexibility layer in the middle where the tenant will come up with a service profile that will also be part of the CSLA, and it will go to something called a CDO service manager. And the service manager is responsible for actually breaking down the services into the microservices and the service graph. In order to understand that where we can find suitable transit for managing or satisfying the requirement of the edges, we'll communicate with the network manager of the CDO, and both the service and network manager will consult with a capability database. And this is a database which is populated by the slices and the services advertised by the service and the transit domains. So after that, we have the same architecture. We have an NSP and an NSA. So now the benefit here is based on a service demand, we can now choose which NSP would be better than the others to conform with the quality of service demands specified in the service graph. On the left, you see a very simplified protocol map. So these are all RFCs and standards which are provided here, and these are references of the paper in the UCNC that I also referred here. So software-defined networking provides something called the abstraction of the network. So we create an application view of a network, and we rely on various components in the SDN to translate that application view of the network into flow-level instructions. Those abstractions can be leveraged by policy-based routing defined in RFC 1104 for enforcing routing in the layer 2 or layer 3, overriding their native routing protocols. Now, why is it important? Think of a wireless link. The parameters of wireless link is something which is not covered by any of the routing protocols. For example, EIGRP, which carries the longest or the most complicated functions to calculate metric, it uses bandwidth, delay, load, reliability, and MTU, and jitter for the newer versions. But it doesn't consider RSSI. It doesn't consider path loss. So what if I have a wireless link in the middle and those parameters are important to me? I have no way to explain that to a typical routing protocol. This is where policy-based routing can be useful. So we can create whatever metric formulation we need. We just need a number that help us to rank the routes. How that number is derived is very arbitrary. So we can create an arbitrary function with whatever attributes we need. And based on that, we can formulate a metric. Once we do this, then we can move on to the slicing. And we just explain that what a slicing architecture looks like. So we comply with the standard, and we can then link it to 3GPP model. Now, most of the transport networks are based on the IETF standards, and therefore, an IETF RFC, which is ACTN, named after abstraction and control of traffic engineered network, can be useful. And this is also identified by ETSI that this is the most suitable standard through which slicing can be implemented in transport networks. Now, traffic engineering is not a new thing. It has been there for, I don't know, for around like 2 or 3 decades. The classical way of doing traffic engineering was MPLS-TE, which in turn used something called a protocol called RSVP or reservation protocol. But newer versions or newer approaches which are also coming up that addresses certain issues that comes with MPLS, for example, state management. So SRv6 is a new approach, which is segment routing over IPv6. It does not need any extra control plane on top of the forwarding. So routing can be encoded into something called a segment list inside IPv6 packets. And there are works which are going on and new standards are coming up. Some of the papers are also claiming that SRv6 could be way forward to upgrade GTPU completely in the next generation. But they're all claims. We haven't seen any standards coming from 3GPP so far, but there are evidences in the literature. So task-oriented networking, what I explained in the very beginning of the presentation, works like this. So you have a cross-domain orchestrator, and you have a set of intra-domain orchestrator. And this makes a hub and spoke model. So that makes it hierarchical. Now, each of these administrative domain manages their own infrastructure. So all the policies running inside the infrastructure is within their administrative boundary. And we know from the BGP's RFC that administrative domains or autonomous systems should not influence other autonomous system how they want their traffic to be managed. So therefore, the CDO sits on top of it, having overarching view of the underlying inter-domain orchestrators, and it performs something called a task-oriented computing or task-oriented networking. The task here is an extension of an intent. We are familiar with the intent-based networks. So task is also, what if the intent is incomplete? What if there are certain information which might not be realized by the intent provider? Task-oriented networking says, okay, so let's communicate with the intelligent entity, which we call the AIO here, which is the knowledge plane in this case, to reason some of those missing parts and fill up and then get a better service. Overall, this architecture is cognitive because we have access to certain reasoning capability, and this is very, very stakeholder driven. The paper I referred before for the CDO has a full description of this architecture and the various components of it. So with this, let's move into the modeling of the network dynamics. And this is something I will go a bit slow because this will unify the concept of this ground space continuum that I initially discussed. I'll go through these steps to model a dynamic graph. The mathematical model that we are aiming for is the spatiotemporal continuum of a non-Euclidean space. Non-Euclidean because we are dealing with graphs, and graphs are not Euclidean. Therefore, we need to map them in a non-Euclidean space. And it's a spatiotemporal continuum. If you recall the organic networking perspective, the graph changes in space and time domain simultaneously. So you can add new nodes, you can change topology, or you can also have isomorphic transformation. At the same time, the values or the attributes associated with the links and the nodes, they also change over time. So think of a very simple three-node mesh, V1, V2, and V3. Each of them carries a feature vector XV1, XV2, and XV3 typo here. It should be XV2 and XV3. And the edge features, which are XE12, XE13, and XE23, respectively, for the links. Now, this is what is referred to as a snapshot of a graph. So we capture it at a given instance of time, and there's a time axis that has multiple instances of those. The task here is it possible to look this problem as an autoregressive problem? And can we find a learnable which learns certain features or certain attributes from this continuous process, and it gets certain inferences from it? So the following would be a list of equations and the modeling of this problem in a more succinct way. We first start with the transit topology. So a transit topology is a graph of vertex and edges, where the edge set is a pairwise vertices. So it comes from the V square. And the number of vertices we have is n. That makes the edge set bounded in n-1 to nc2. And for n-1, it will be a tree, nc2 to be a mesh. We next look at the UPF association. So the Open vSwitch or layer 2 topology that we have in the data plane of the SDN, they will communicate with the UPF of the user plane of the 3GPP 5G core architecture. So a mapping function can be imagined, which is MUT, that takes a UPF vertex VU and map it to a subset of the VT. So we are thinking of a multi-homing connection. So one UPF can connect to multiple switches. Now, in the RAN side, we also have G node B association and RAN topology. So G node B association says which G node B is connected to which UPFs. Here I'm considering one G node B connects to one UPF only, so the mapping function is a one-to-one. The RAN topology is a graph, and this describes the XN interfaces in the RAN. So GR is the graph, and it has some vertices VG and some vertices, some edges EG, depicting the topology of the RAN. Now, based on this information, because we have the mapping functions to map the G node B to UPF and the UPF to the transit network, we can now conceptualize a metagraph which can take the transit topology, the RAN topology, the mapping of UPF and transport, and the mapping of G node B and UPF all together to create a unified graph structure. This is to simplify the model, because once we get this graph structure, then we can use this for training. Now, when this graph evolves over time, we get something like this. It's not a snapshot, but it's a sequence of snapshots. So this GT is the graph snapshot taken at the tth instance of time, which carries the vertex set at tth instance of time, edge set as tth instance of time, with the feature vectors. I would say the feature matrix, because the XV and XE, the dimension of them are the number of vertices or the number of edges they have times the number of attributes for the vertices and edges respectively. And because this is one instance and you have multiple instances of those, you end up creating a tensor. So these XV and XCs are real tensors of order of the size of the vertices, size of the attribute of the vertices, and time, and same for the edges. So with this representation, what we get is a continuous or a discrete snapshot of graphs which are evolving over time. This is a very, I would say, lucrative recipe for thinking of latent space modeling. So we can now think of a learnable which could take this dynamic evolving metagraph as input with a given window size and map it to a d-dimensional real space. This is the real space from which we'll draw our reasoning. Now, the non-Euclidean geometry comes here in the form that this graph in its form cannot be directly given for a learnable, because in a non-Euclidean space, there is no definition of distance. If I provide you two graphs and I ask you how they are different, there is no real measure between them. So we need to map them through their Lagrangian first before we kind of do those calculations. And this is something, is a well-known work in the graph neural network. Back in 2006, the first paper from Gori was published that described this whole modeling of this mapping. And then on, we have various examples of it. One such example is this paper. It's last year JSAC publication. They used a graph neural network to place VNFs in a zero trust manner in a sliced network using SRv6 at the data plane. Now, where this AVs and AE comes from, these are the two set of variables defining the attributes of the vertices and edges. These are defined via some convex optimization functions. So think of these AVs and AEs as the set of free variables associated with the nodes and the links, associated with some cost variables. And we define a very simple generic convex optimization problem with set of constraints and set of boundaries. So with this, we have an overall view of how a generic topology would look like, no matter if it is just 5G core, 5G UPF topology or 5G UPF topology connected with a switch topology. Now you can also extend this with NTN, because in NTN, it doesn't matter if it is a regenerative or a transparent mode operation. It's just an extra node in the graph. And the link features and the node features are corresponding to whatever type of links we are using or whatever type of nodes we are using. So this model generalizes the concept of this edge cloud space continuum into a spatiotemporal graph that changes over time. So from this, there are various optimization tasks that we can perform on such graphs. One example is routing as a service. We've been working on this since I've been working for this since my PhD time. So some of the notable works are here. In 2024 IFE, we published the full stack architecture. I'm going to show you the demo of this today. So we have the data plane and the control plane and the application plane, and you can see different tools that we use to build it. And a recent paper that is also accepted this year in COMAD that describes the heterogeneous networking. So think of the data plane is not only comprised of switches, but what if there are switches, there are other routers, there are, let's say, G-node Bs carried in the satellite. So in that case, the data plane itself becomes very segmented in technologies. So we introduce a concept called topology fusion, in which different type of topologies can be fused into a larger metagraph. So this is an example of a metagraph. I'm not sure if it is visible or not, but the green nodes here, they represent routers with their IP addresses, and the red nodes here, they're open flow switches connected to hosts. Now you see the host connected to the red nodes, which has only MAC addresses, whereas the nodes connected with the green nodes, which are hosts with IP addresses. So we demonstrated that through this, we can create policy-based routing from a layer 2 domain to a layer 3 domain across two different routing domains through this pseudo node. And he also performs certain benchmarks of Dijkstra's algorithm, A-star algorithm, all shortest path algorithms. And the scale of the topology, we scaled from 36 to 94, which is a considerably larger topology as far as the real life networks are concerned. But the time taken for this the full closed loop operation is below 1/3 of a second. I will show you in real example in a moment with demonstration that how is it possible. The main reason why we are saving time is we are completely eradicating the control plane latency in the network. So in order to do routing, traditionally what people do, or traditionally what routing protocols do, is they exchange control packets between each other. And the time consumption of this control packet exchange increases as the network diameter increases. So as a result of it, a link failure far away from a service needs to be informed to the node which is connected to the service across this entire diameter. And unless the network completely gets converged, it doesn't send any traffic. So this is where the time consumption comes in. Secondly, because of these routers which are used, their processors are not general purpose processors. So it's very difficult to scale the supervisor's computational capability very easily. Whereas if we can take all these control plane functions into a central point and running them in x86, 64 kind of hardware, then it is now easier to scale up and scale out as the resource increases and the demand increases. So this is a recorded demonstration, not the one that I promised for the live demonstration. What you see here is on the right, I'm running Lens, which is IDE for Kubernetes, and it is running RAS. On the left, you see 4 application that runs the RAS application in action, and see the path computation on demand. So let me just play this. So first of all, we will go to the pod section and we'll see there are 4 pods running. Or should I change this to a pen perhaps? Yeah, okay. So if I go to the pods, I see there are 4 pods running, and these 4 pods are the client the server, the OpenDelight controller, and the mininet for emulating the data plane. So these are the four pods, and they're all exposed as services, as you can see in the service section here. And these services are exposed over RESTful APIs, and they're accessible in the port number 8001, 23, and 8181. I'll first start with the application, which is this topo build application that we built as a wrapper on top of Mininet. So instead of typing Mininet command, you can give basic information like if you want to build a topology of 5 nodes and 2 switches each, and you provide where the controller is. It will create a topology file, and because the topology was running, so I had to stop it first and then generate and deploy. So once the topology is deployed, then Mininet will create an emulated Open vSwitch topology, which you can verify from OpenDelight through the LLDB discovery process, and you get the topology here discovered. Then we can do a ping all to do a broadcast in the network, and this will discover the hosts in the OpenDelight topology. And now we go to the RAS client, and here we say where the controller is, which is 10, 120, 51, 51. This is the application plane, by the way. We can fetch topology from the controller, and the topology is represented as an adjacency list. We can also draw them to see the visualization. Now, after this, we can process this topology. So one of the processes that we can perform is finding the shortest paths. Now, the attributes are at the moment arbitrary. They are not in effect. But the idea is whatever attributes you put, they must be equally weighted initially, but you can also change the weights. Then we can define what algorithm we want to run for shortest path. It just got all the paths for all the nodes. This is extremely useful because now we are not only seeing the local routing information base, but the global routing information base of all possible paths between all pair of switches. Now, think of how can we use this information. This information can be ranked based on the cost, and this could be used for a constant time convergence. So if a particular link fails, we can straight away go and query this database that what is the next available routes, and we can get that route and configure it on demand without exchanging any control packets. So with this, that's an example of building the application plane and doing routing as a service. And this also justifies the very low latency that we achieved in benchmarking this application in the previous slides. So for the live demo, the setup that I'm using is this. I have a remote pair of VMs running ODL and Mininet. They're communicating with the OpenFlow 1.3, and they are emulating the data plane and control plane of the SDN. They are connected with a subnet, which is 10.120.59.0/24 with respective IP 60 and 61. I am connected with this subnet over a VPN. So I'm running a notebook locally, and this notebook will do get and post to read from and write into the REST operational and the REST configurational APIs provided by ODL. This notebook is leveraging 3 major libraries: Request, NetworkX, and LangChain. So Request libraries is to make these HTTP calls. NetworkX is for the graph theory calculations. Now, the part that I will not cover in this presentation due to shortage of time is the application of LangChain. Now, in my case, the whole setup is running in my local computer. So I am using LM Studio as a software to host a Gemma 3 4 billion model. And LM Studio exposes this model in port 1234. And I can access that model from LangChain. So I can build agents in LangChain, and I can use this way to communicate with the model to do some reasoning. So the way it is work that based on the application plane, if we create tools, these tools will be basic functions which would do this get and post requests to retrieve or change things in the network state, and these tools would have certain kind of descriptions, and these descriptions will be used by the LLM to reason in order to satisfy a particular task, in which order which tools will be invoked. So this is the I would say the integration of having a knowledge plane in practice on top of an application plane that communicates with the control plane in a closed loop, and the control plane manages the data plane with OpenFlow. Before I move to this slide, let me show you the demo very quickly. So as you can see, I have got a couple of CLI running. So this is the OpenDelight controller, which I think I've lost connection to. That doesn't matter, I believe, at this moment. Yeah, I need to actually create some new sessions. Give me a moment. So I will log into these remote servers. Okay. So 5960 is where my OpenDelight controller is. And I logged in, and just for the sake of, hello, am I audible?
Yeah.
Okay. All right. So for the sake of simplicity, I will restart my OpenDelight controller to start things from scratch. I will log into my MiniNet VM, which is running in 61. And I will remove whatever topology I had before. Okay. So we are in a clean slate now. Just to check if everything is running, I can go back and see my topology gone, because my MiniNet has cleared the topology, so everything is running okay. So starting with the reachability, both my VMs are reachable. I can get ping response from them. I am getting some topology information. So yeah, I'm not getting topology information. I have to first do something in MiniNet to get the topology information. So what I'm going to do here is I'll run a very simple command, which is this. I am saying MiniNet that run a topology of type linear 5, which is a series of 5 switches, and I'm setting the controller, which is at 10, 120, 59, 60 at port number 6633, and I'm saying my switches are all Open switch switches running with OpenFlow version 1.3, and all of them has sequential MAC addresses. Once I run this, it goes and communicates with the controller. It creates links and hosts and everything, and I can go to my controller and I can do some refresh, and I can see LLDP discovery has discovered the topology. I can now do a ping all to do a broadcast, and this will also discover my hosts. This is something you just saw in the demo through that wrapper application we built, so you don't have to type the commands like this. And that RAS application also allows you to create custom topologies. So after this, we go to the section 2, or the task 2 of this notebook, where we get some libraries installed, and we use NetworkX library to do some basic plotting to verify if everything is running. And then we'll use a request API, or request library, to call the RESTconf endpoints of my OpenDelight controller. So you can see that I'm communicating with 10, 1, 20, 59, 60, 81, 81 interface, and it's operational API I'm calling. So I'm getting the read-only information from it. Once I do this, I get a 200 back. So the response was successful. And I can now use a NetworkX library to not only see the flow level information, but I can also, let me just make this a bit wider. Okay. I can also plot the topology like this. So what I have done, I have taken the topology from OpenDelight and mapped it into a graph object. It's a directed graph labeled with whatever information is coming from the ODL controller. So I can manipulate this graph. Things I can do in this graph, for example, I can see how many hosts I have. I can create paths for every pair of hosts. And I can create something called a path information base. So path information base is starting off a source and a destination. What are the available paths? And this path information base can then be translated into what I call a global routing information base. So routing information base, or RIB, is something that runs inside a switch or a router. But global routing information base is the collection of all routing information base of a network. This is the information will then get split into switch-specific instructions, and I can also plot them in tabular form like this, and then I can send this information into the switches. So this function, flow injector, it injects those flows into the configurational APIs of the OpenDelight controller. Now, if I run this, what you will see that all these grids are then gets injected into the specific switches, and all of them gave me 200 information. And finally, I can verify that with some extra scripting, and I can see a live view of the flow tables of every single flows of every single switches. They are configured based on the policies that I derived from the shortest path functions from the NetworkX library. So this is the demonstration of connecting an application plane with data plane and a control plane. As I said, knowledge plane I wouldn't be able to show at this moment, but that setup that I showed, if you follow the same setup, you would be able to now create these codes into functions and then decorate those functions with tools provided by LangChain. And these tools can then be used by the LangChain agents to get invoked whenever it is required. And for that, it needs a very simple language model. I'm using a Mac, and I'm using a 4 billion parameters model, and it is running smoothly. So, I mean, you can run this whole thing in your local setup, and if you have better GPUs, then it might get better performance. Okay, so coming back to this slides, I'll finally talk about a bit of the state of the art of these works. So where are we at the moment? What are the literature suggesting? How do we tackle these kind of problems? So the AI native in telecoms is a new thing. Everybody is working on that. TPP is interested. But in the literature, I find there are two major categories of work. One which is seeing this problem from a classical dynamical systems modeling. So papers like stochastic service curves and the control differential equations. These are the areas where the model is more continuous in nature. So if you remember the background that I showed in the slide, that is an example of a vector field, and this is how the blue team is approaching this problem. Very interesting work from the Turing Institute. They offer graph path theory, which is also taking the same kind of aspect or approach to tackle this. But the other side, which is more compatible with the 3GPP and HC standards, is to see the problem from a graph foundation model. So basically, these graphs that are transiting through some kind of transformation, these can be captured into sequence generator functions. And this is also suitable to be done through a transformer model with attention mechanism. So as a result of it, if this knowledge can be captured, this can be captured into a foundation model, and this foundation model can be then transferred. So this foundation model, as I'm using, for example, the GEMA model, which is a foundation model for my language translation tasks. Similarly, this kind of foundation model can be useful for predicting the state of a graph or doing some semantic analysis on those graphs. There are several works which are going on at the moment. Transformers are being discussed recently. All these papers are from the last 2 years or 3 years of their publications. Um, there are many optimizations which are being made, like graph summarization and the expressive power of graph that says what are the different things you can do with a graph. So these are the theoretical part of it, okay, which is useful for modeling, for example. The practical part of it comes from standards. And there are mainly two groups of standard that I have classified for this presentation. One is network digital twin. There are two main projects that I would like to cite here. One is 6G across, where Telefonica provided a network digital twin for security analysis of unseen behaviors of a network. And a newer project called 6G Twin, which is led by LIST, Luxembourg Institute of Technology, and here VIAVI is providing a network digital twin. And I would say this architecture is much more matured compared to the initial architecture provided by the HC ZSM proof of concept work. You can find the explanation of network digital twin in the ITUT 3093 document. It's an ITF draft as well. There is a release 20 draft or release 19 draft, to be honest, which has description of network digital twin and management of network digital twin. HC also comes up with different use cases for it. So the draft that I was mentioning is 28561, release 19 version 1900. This is where you find how 3GPP is approaching network digital twin and how they see it as an option. Some research ideas like the self-attention mechanism with dual attention mechanism is also proposed in order to tackle network-specific tasks. Because one of the major problem of having AI in a network is trust. So, for example, if some operator kind of gets approached with a network digital twin provider saying, "Oh, I will put a AI on top of your network and it will handle all your network," that's not a feasible proposition, because if the AI makes a mistake, if the AI does some kind of hallucination, by the time the network manager understands or realizes this has happened, billions or trillions of bits are misplaced. So therefore, we need a closed loop model with human in the loop. So more detailed description which are provided in, for example, ITUT 3093 that describes how this kind of human in the loop can be approached. This ITF draft, this maps the concept of ITUT's document to the ITF standard, so you can actually map the actual protocols which can be used to achieve it. The other part, which is very recent, as you can see, the document was published in 1st of January 2026, is the HC ENI. ENI stands for Experiential Network Intelligence. There are 4 or 5 reports that have come, and I've picked up 3 of them. One is the actual architecture of what ENI is, and there are some options of communication, some classes of communications are defined. So what ENI says, that think of an existing infrastructure as an assisted system, which may have intelligence, may not have intelligence, but ENI can be provided as an external intelligence, which would communicate with this infrastructure through some kind of open APIs. Then a specific type of large language model is also proposed, called the network knowledge enhanced large language model, or knowledge enhanced network large language model. These are specific model trained with network configuration information, because unlike typical texts or literature, Technical documents are much more structured. Technical configurations are much more structured. So it's easier to train a large language model with those sources so that the hallucination can be minimized. And the specific way of doing this kind of training is defined in this section 5 of this document ENI 041, and then a list of use cases, what kind of services you can think of when you have ENI attached on top of a network is described in the ENI 001 document, which is very recent, May this year it came. So with this, I conclude my discussion, and the final remarks is, you might have noticed there is no discussion of NTN at all in this presentation. So where does the space come from? The idea is, if you see from the network orchestration point of view, we really don't care. We see a graph that changes. That graph represents a topology of a network. So no matter if it is a regenerative or a transparent mode integration of NTN, it's just a graph. So from the NTN, so the orchestration point of view, it is just a graph. So that will be a unification of, or a generalization of, let's say, a spatio-temporal transformation of a dynamic graph. With that, I conclude the discussion, and I'm happy to take questions. Thank you.
Yeah, thank you, Saptasi. I don't know if there are any questions. Let's check the Q&A session. I don't know. I have any questions? I mean, probably I can ask a question about this adoption of segment routing. I mean, okay, it is still at the research level. So what is, how is likely to be adopted towards an integrated NTN architecture?
Yeah, sure. So segment routing, let me just recall if it is at all possible for NTN. So segment routing requires IPv6 data plane. So if, for example, the G-node B sits in the satellite and we get a feeder link from the ground station, this will eventually carry a GTPU tunnel. So this GTPU tunnel would run UDP on top of some kind of layer 3 transport. So this layer 3 transport would be IPv6. So in that way, unless we have a requirement of, let's say, topology of G-node Bs in the sky, I don't see a point of doing routing in the space. However, segment routing can be used to switch between terrestrial link and satellite links. So, for example, if the topology metagraph describes that a satellite link, it might be feasible compared to a terrestrial link, then segment routing can be used to kind of craft a segment policy in the IPv6 packets. So when those packets enter in the network, they know that at this point of time, I will take the route towards the feeder link, not the terrestrial link. So this is one aspect I can see where this can be useful.
Mm-hmm. Yeah, good. If you check on the Q&A, there is a question.
I see the last one from Way only.
Yeah, this is the one.
But is it for me or is it for the last presenters?
No, it's the
Oh,
the
yeah.
last one. Okay.
Got it. So the question, question regarding your live demo, since the network X is already computing for this part, realistically, what specific decisions? Yeah, very good question. So the idea is this: if you understand how the LangChain agentic framework works, so routing is one of the task, right? You can have different type of functions for calling different routing algorithms, or shortest path algorithm, to be honest. So the agents will see the description given on those decorated functions. So for example, if I give a prompt that show me all possible routes, which prioritizes path loss over latency. So it will go and see from the descriptions which among those existing decorated functions have some notion of path loss. So choosing between those tools is what the agents do. They autonomously choose the agency through which they access tools. So the application plane, for example, network X library is an example. We can create all possible type of algorithms we can call from this library. But when a task comes, the user might not be sure about in what exact manner they would be invoked. This is where the intent can be parsed by the large language model to identify which calls to make and in which order to make those calls. And then those calls are actually eventually made to the application plane. I hope that answers your question.
Okay. All right. I think we almost reached the far end. We are, I think we are half an hour late. I would like to thank all participants and also thank you, Satas, again for your excellent presentation, giving the insights, all right, in network automation. All right. Thank you all. Thank you.